There's a bacterium most of us carry around called Haemophilus influenzae, and we usually don't give it a second thought. That's mainly because of a vaccine that was a huge public health victory. But what if that victory actually created a blind spot? What if it let a new, much smarter version of this bug sneak in under the radar? Well, new data is showing that it's been quietly learning how to fight back against our medicines, and the results are pretty alarming. And that's really the big question we're digging into today, isn't it? This is a full-blown evolutionary arms race. We're about to break down how one of our oldest foes just got a serious upgrade, rewriting its entire defensive strategy right under our noses. All right, so first things first, let's talk about the bug itself, Haemophilus influenzae. If that name sounds familiar, it's probably because of the Hib vaccine. A lot of parents will know this one. It was such a massive success that, honestly, we thought we had this thing beat. And let me tell you, this vaccine was an absolute game changer. It went after a really specific, super dangerous version of the bacteria, the type B strain. That one strain was responsible for over 90% of severe infections, like meningitis in kids. The vaccine literally saved countless lives, no question about it. But, and there's always a but with nature, right? Nature doesn't like a vacuum. So by wiping out that one big bad strain, we kind of rolled out the red carpet for another version to take its place, the non-typable strains, or NTHI. For a long time, we thought these were just harmless little bugs living in our noses and throats. Not anymore. Now they're a major cause of serious invasive infections, and they've brought a whole new playbook of problems with them. So what's the deal with these new strains? What makes them so much more dangerous? Well, it all comes down to how they've figured out a way to survive our best antibiotics. They've literally rewritten their own defensive code. Let's get into how they're doing it. Okay, so to really get this, we first have to understand how the antibiotic is supposed to work. Just think of it like a simple lock and key. The antibiotic, in this case ampicillin, is the key. It's perfectly shaped to fit into a special lock on the bacteria's wall called PBP3. When that key goes in and turns, it busts open the cell wall and poof, the bacteria is gone. Simple, right? Okay, so bacteria have gotten clever in two main ways. The old school form of resistance, called BLPAR, is kind of like putting up a shield. The bacteria makes this enzyme that just smashes the antibiotic key to pieces before it can even get to the lock. But the new way, well, it's way more subtle and way more worrying. It's called BLNA. And with this one, the bacteria doesn't even bother with the shield. It just changes the lock itself. It mutates the gene for PBP3, so our antibiotic key doesn't fit anymore. The drug is now completely useless. And just when you thought it couldn't get worse, it does. You get the worst of both worlds scenario, a super strain called BLPACR. These are the bacteria that have it all. They've got the shield to destroy the antibiotic, and they've got the changed lock on their cell wall. This 1-2 punch means they can beat even our smarter drugs, the ones that were designed specifically to get past that shield. So how big of a deal is this, really? Is this just a local problem? Well, thanks to a massive global study, the Century Antimicrobial Surveillance Program, we now have a really clear and, frankly, pretty startling picture. They looked at almost 14,000 samples from over 50 countries. All right, so let's look at the data. What you're seeing here is the prevalence of those BLNA strains, the ones with the changed lock. And the trend is just, it's impossible to miss. While rates in Europe and the Americas are kind of hanging out in the teens, you just have to look at the bars for Asia and the West Pacific. For countries like Japan, Korea, Taiwan, they're soaring. We're talking 60, 70, even 80%. The research doesn't say exactly why, but this kind of geographic hotspot often points to things like regional antibiotic habits, creating this intense pressure for the bugs to evolve. And if you want to see just how extreme this can get, look at this. In Vietnam, a staggering 87.5% of the strains they tested had this changed lock mutation. Let that sink in. Almost 9 out of every 10 of these infections are caused by a bug that has totally outsmarted one of our most calming medicines. And the story gets even grimmer when we look at those super strains, the ones with both defenses. The pattern is hauntingly similar. Again, the highest numbers are all clustered in Asia and the West Pacific. In places like Korea and Japan, more than a third of infections are caused by a bug that has both the shield and the changed lock. I mean, can you imagine being a doctor on the ground facing that? It's a huge challenge. Okay, so the resistance itself is a massive problem. But there's another layer to this that makes it even more dangerous. The problem is, we're often flying completely blind. Our standard tests are missing the most critical part of the story. And here's why. The go-to rapid test that so many labs rely on is called the nitrocephin test. It's designed to do one single thing: look for that enzyme shield. That's it. It has absolutely no way of telling you if the bacteria has changed its lock. It has a major blind spot. And this quote from the study just nails the danger perfectly. If your test only looks for the shield, you are going to completely miss all the change-lock BLNAR strains. And even worse, you'll get a misleading result for the super-resistant BLPACR strains. You'll get a report that creates a totally false sense of security. So let's just walk through what this means for an actual patient. Okay, someone comes in with a change-lock BLNAR infection. The lab runs the standard rapid test. The test looks for a shield, doesn't find one, and reports back a negative result. So the infection gets labeled as susceptible, easily treatable with ampicillin. But it's not. The lock is changed. The doctor prescribes a drug that has zero chance of working, and the treatment is doomed to fail from the start. So where does all of this leave us? Well, the bottom line is that the rapid rise of these changed lock mutations means we have to urgently rethink everything. Not just our treatments, but our whole approach to how we even diagnose and track these infections. And here's why it's so incredibly urgent. That little mutation that changes the PB3 lock, it doesn't just block ampicillin. The research shows these strains are way more likely to be resistant to a whole bunch of other critical antibiotics too. We're talking cephalosporins, tetracyclines, even fluoroquinolones. Our toolbox of effective drugs is shrinking, and it's shrinking fast. So what's the takeaway here? What do we do? Well, the path forward is pretty clear. First, we need much better global surveillance so we actually know what we're up against. Second, we have to update our diagnostic tests to get out of this nitrocephalin trap. And of course, it always comes back to using antibiotics more carefully, from doctors to patients, to just slow down this evolutionary race while we scramble to find new ways to fight back. You know, at the end of the day, this whole thing is a story about adaptation. Bacteria are masters of it. They are constantly evolving, constantly rewriting their defenses to survive. So the real question this leaves us with is, can we adapt our medicine, our diagnostics, and our global strategies fast enough to keep up?